too late to start. So I'm going to try this one more time. Hopefully, next Tuesday, my voice will be back to normal. So the reason we're a little bit late is I'm going to try an experiment today, see how it goes, and a video record the class. I'll post it most likely on YouTube. If it looks like it works well, I'll continue doing it. Yeah, you don't need to do that. And maybe it'll be a useful resource. So I'll see. I'm not convinced the quality will be sufficient that it's helpful, but again, we'll see. So, with that said, a couple of quick things, and then I'm hoping to get back into physics relatively quickly today. You'll have seen a few emails from me over the past 24 hours, something like that. The one that I'm most wanting to follow up on right now is the issue of textbook, because I'm aware, as often with these online resources, that there's possibly some confusion about the formats and so on and so forth. So, bottom line is we will be using Mastering Physics for the course, so you do need access to that. You'll have seen in one of the recent emails a link to a page from the publisher, Pearson. Again, they're complicated, confusing, but I think what you need is the Mastering Physics access code, and there's a modified Mastering Physics, which I don't know what it is, so ignore that. Mastering Physics access code, and if you so choose, you can also choose to get the eText along with that. So those are two different packages. One is Mastering Physics standalone, and the cost was something like $68, I think. And then the other was Mastering Physics with the eText, which is maybe $115, $120, something like that. Of course, there are also print formats available. I'm intending to downplay those, simply because in general the cost is much greater. But if you wish to have a hard copy book, of course, you're welcome to do that. So I just wanted to pause and just air this a little bit, because I'm aware still there's some confusion. So let's see what sort of questions you have and if I'm able to answer them. Yeah.
So for the standalone one, is it for only one semester or is it for both semesters?
So I think it's for both semesters, and I'm fairly sure that I saw confirmation of that on the web page that I sent the URL to. I have to confess, I'm never hugely confident in what I hear from the publishers. Pearson, I think, is one of the better ones, and they're more responsive than some others, but my understanding is it will carry over into the second semester. Other questions on this textbook Mastering Physics issue? Okay, I take that as a good sign, hopefully. If you do have any remaining issues, let me know. I'll try and find the answers to your questions, but it sounds like things are starting to settle okay. Good. So then I guess the only other question is any other sort of questions on generic things about the course so far, coursework, all that stuff. I heard from somebody just before class that they were having difficulty with access to courseworks. Any other problems that have come up? Yeah.
Is there like a specific reason for
so the question was, is there a specific reason we need the 14th edition? So usually what happens between different editions is some aspects of the material, most significantly the problems, which we'll be using for homework, change. And obviously since we're using Mastering Physics allied with the 14th edition, I'll be studying the problems from there. So I think if you want to have, let's say, a copy of the textbook that is older, I think that's fine. But in terms of the Mastering Physics access, that would need to be allied with the 14th edition, just so you've got the correct homework problems. Does that make sense? Good. Any other questions? Excellent. All right, so let's jump in. I'm going to talk a little bit about dimensional analysis and vectors for the first maybe, 15 15 minutes of class, and then we're going to jump into looking at motions in one dimension, so kinematics. And as we jump into that first sort of true physics section, we'll be starting looking at variables, quantities that I'm sure almost all of you have come across already when we talk about describing motions. It's talking about positions, displacements, velocities, accelerations, and we'll be rather fast in defining these things, because again, I'm expecting most of you have seen this before. At the same time, for those of you who haven't, I'm hoping it's detailed enough that you'll be able to follow along relatively quickly. And then, if we manage to get to that point, we'll talk about the specific type of motion when an object is undergoing constant acceleration. And ideally, that will get us through today's class. So, let me first off start talking about dimensional analysis. And it also ties in with the concept that in any sort of equation that we're going to be using in physics, we ought to have dimensional or unit consistency within that equation. And I think the best way to sort of describe that is simply by example. So I'm just going to give a few definitions, and then I'm going to actually ask you guys to work through a simple example of dimensional analysis. Okay, so we start writing. Unit consistency. And it's very much allied with this idea of dimensional analysis. And I think I'm going to cut this somewhat distracting projection. Okay, so we're talking about equations typically, but more generally about relationships between different variables in some physical system. So let me start out by saying that equations must have unit consistency. And I'm actually already here going to put the word dimensional consistency. And this is going to turn out to be a very useful cross-check to make sure we're not screwing up. But it's more powerful than that. It's also a method for determining, you describe this as the dependence of one parameter on others in some physical system. So it's also a method for determining the dependence of one parameter on others. And I think I'm going to put others in quotation marks. Requires a little bit of insight to understand what that might mean in some physical system. Okay, so we need to talk a little bit about what we mean by dimensions. I'm going to go on to a huge chalkboard here. Maybe I should really call this dimensionality. Okay, so what do we mean by this? We already talked about last session the idea that units for various measurements may be different, even though they're measuring some underlying common physical parameter. Let me take the example of distances. Here in the US, we're most commonly describing distances in miles, maybe yards, something like that. Elsewhere in the world, and particularly places that use the SI system that's most dominant in science, you'll find people using meters and kilometers, okay? So these are both unit scales, unit systems for measuring distances or lengths. So while the units differ, the dimensionality is the same. The dimensionality is that underlying base variable that we introduced last time. It's length in this case. So it's the sort of underlying, it's hard to describe this without using circular language, but it's the underlying dimension or maybe base quantity, base unit, that may be measured or quantified in different unit systems. so I mentioned the possibility of using miles or kilometers, but generically the dimensionality is length. And when we talk about dimensionality, we give it a special notation, and it has these sort of square brackets or square parentheses around it like this, okay? So for anything that's a distance or a displacement, as we get a little bit more technical later in the class, the dimensionality of that thing is length. And we're going to describe it as something like this. We've also got time, of course. Typically, we write this as capital T, again in square parentheses. And so far, the only other base parameter that we have is mass. And so dimensionally speaking, we're going to represent this as a capital M, again in square brackets, okay? So these are our sort of base dimensions, if you will, the only ones we're going to be using for a while. And as we talked about last time, we can of course start introducing parameters that are a little bit more complicated than just distances or elapsed times or so on and so forth. And the example that I introduced last time was velocity, which is some sort of displacement. We're going to be defining these terms more formally in a few minutes, but it's basically a displacement over elapsed time. So distance over time, perhaps in more shorthand. And dimensionally speaking, then, this would be a dimension of length over a dimension of time. Pretty straightforward. We might also write this as L T to the power minus 1. Okay? So all pretty basic stuff. Obviously, you're going to expect that the equations you use have this sort of unit or dimensional consistency. In the thick of calculations, you may be tempted to drop units. I certainly am, because it's kind of a pain to always write them down when I'm doing calculations. Up to you if you want to do that, but make sure at the end of some calculation, you go back and check and then write down what the actual units are in whatever calculation you've been doing. So that's obviously important. And again, this is going to allow us a sort of kind of nice cross-check to make sure that when we're doing calculations, we've not screwed up along the way. All right, so let's say we're dealing with quantities that are typically things we're dealing with in Newtonian mechanics, and they are generally based on these basic parameters, these base units. And so as we build up more complicated parameters, we talked about acceleration a few moments ago, we can generally say that some quantity can be expressed as a product of these dimensions. So generically, at least when we're confining ourselves to mechanics, where we don't yet need any more base variables, we can say that some quantity, in terms of dimensions, maybe can be expressed as, and it's not really fair to write the equality here, but I'm going to do it anyway. We can write it as the dimensionality of mass to some power alpha, perhaps, a dimensionality of length to some power beta, perhaps, and the dimensionality of time to some power gamma, perhaps. And whatever these coefficients are, alpha, beta, and gamma, that's obviously telling us what the intrinsic dimensionality of the quantity at hand is. Okay, so we may well also have dimensionless quantities, things that don't have any of these dimensional units associated with them. There are plenty of cases where we'll have dimensionless quantities. And of course, if we do have such things, it means that all of those coefficients are zero. I said this is useful as a cross-check, and it certainly is, but it's also, I think, much more interestingly useful in the second sort of bullet point on the left-hand chalkboard. It allows us a surprisingly powerful tool for figuring out how one quantity in a physical system depends on others. I'm going to ask you guys to struggle with this for just a moment in a simple worked example. So the thing we're going to think about is something that looks not so dissimilar from this. Okay, it's a tennis ball on the end of a piece of string. I'm going to suspend it vertically And, okay, I'm going to let this thing start oscillating back and forwards. So, aside from being a tennis ball on a piece of string, is there a more generic word we might use to describe what you're watching right now? It's a pendulum, right? Now, it turns out a pendulum, albeit surprisingly simple, amazingly simple, can be pretty useful. And as you probably well know, something like this has been used for centuries as a basis of time measurement. And so, okay, this thing is oscillating back and forwards at a certain particular frequency or period. Let's see, it seems to be taking about 2 seconds to go from one side to the other and back again. That's what we call a period of oscillation for a simple pendulum. So the period of oscillation in this case is maybe about 2 seconds. And the question is, okay, if I gave you this system and you didn't really know much about it, would you be able to learn anything about the period of this pendulum and what it depends on about the system? Okay, so this very often needs to be informed by some empirical or experimental observation. For example, if I make the string a lot longer, it's almost double the length now. Qualitatively, what would you say about the period now compared to a minute ago? It's increased, right? It's taking longer. So it appears to depend on the length of the string. Now, I don't have the resources or the time to do a whole bunch of different experiments, but you might well say, without knowing very much about this, you might ask yourself, what other parameters, if any, does this period of oscillation depend on? So you might ask yourself, well, okay, apparently it depends on the length. You might ask yourself, does it depend on what's hanging on the end of it? Whatever it's made of, its material? Does it depend on its mass? And you probably do a bunch of experiments to find out. And if you had the ability to do so, you might try doing this simple experiment somewhere else. Maybe somewhere else on the Earth's surface, or maybe somewhere else not on the Earth's surface. And so there are all sorts of parameters that in principle this could depend on. And you could sort of build up a list of things that it might depend on. But what we still want to do is maybe use something as simple as dimensional analysis and find out exactly what it does depend on. So I'm going to have you guys think about this for a few minutes and actually work with your neighbor. So, here we go. It's a simple pendulum. Now, the question is, what does the period, and to be slightly confusing here, we tend to use the symbol capital T for period, as well as the dimensionality of something that has time. But here it's specifically the period of the pendulum. What does the period T depend on? And how does it depend on it? So, again, this requires a little bit of insight, but let me say plausibly that it might depend on, and we'll see whether it does or not. Well, we know for sure that it depends on the length of the pendulum, little l. There's no way you would know this from the simple observations you just made, but it turns out if you took that pendulum to different places, maybe not on the Earth's surface, it turns out you would find that it differs depending on where you are. And so in fact, it turns out it has some dependence on the local acceleration due to gravity, little g as we tend to call it. And I know I'm jumping a little bit ahead here in terms of physics, but I feel that most of you have enough prior knowledge of this to be comfortable with it. And in a sense, the lack of comfort is a good thing because we're going to exploit it to see if we can use dimensional analysis. So, okay, wouldn't be crazy in my mind, and in fact some early physical philosophers or natural philosophers observing things like this may well have posited that it depends on the mass of the object at the end of the pendulum. And there may be other things in there. But we could probably narrow it down to a few small variables that we think may have some dependence or may impact in some way the period of oscillation. But I'm going to claim that I'm going to pick these three things as possible variables on which the period of a simple pendulum depends. So, without giving you much more insight into this, I'm going to have you think about the following. So, the period of a pendulum, not to be too confusing here, is capital T, but it also has dimensionality, capital T. And I'm going to hypothesize that it depends on the mass of the object. It depends on the length of the pendulum, and it depends on the local acceleration due to gravity. So the question that I'm going to present to you is, using dimensional analysis, can you figure out what that dependence is? Okay? So for those of you who've never seen this before, it's probably baffling. That's okay. Some of you may have seen it before. What I'm going to do is give you guys 3 minutes to work with 1 or 2 neighbors and see with just this as a starting point if you can figure out how the period does depend, if it does, on these quantities. So it's intentionally not giving you a huge amount of guidance. Talk to a neighbor for a couple of minutes and then we'll work with you through it. Okay, go.
Pretty sure.
Okay, so I think I don't see too much conferring any longer. So what's our strategy? Okay, well, what we want to do is put in what we know about the dimensionality of these three parameters, And then we have to look at the consistency between everything in our equation, so to speak. So, in terms of mass, it's obvious. This is simply as dimensions of capital M. Length, again, simple, as dimensions of capital L. Acceleration due to gravity, and again, we're jumping ahead a little bit here. It's what we'll talk about formally in about a half hour. But this is an acceleration, in fact. So it is a rate of change of velocity with time, and velocity itself is a rate of change of position with time. So if you fold all of that together, and if some of you are doing physics for the first time, this may be a little bit of a stretch, but probably not so much. This has dimensionality of L t to the minus 2, right? Because it's a distance over a time over a time. So L t to the minus 2. Just pause there and ask if anyone has some questions about this. Again, it's a little bit of a jump ahead, but we'll see in a little while. This is the dimensionality of an acceleration. So now we have this, and the question is, what can we do next to figure out the true dependence of the period of time? Well, we need to have unit consistency on both the left and the right-hand side. So here we have n to the power alpha on the right side. There's no n here. So that tells us, right off the bat, that alpha equals 0. I need that to maintain dimensional consistency on both sides of the equation. All right, straightforward enough. If I'm left then with that, let me open this out a little bit more. Maybe I'll go over on this side. I'm going to drop n, because we've already determined that alpha is 0. And I'm going to write this as L to the beta times L to the gamma times t to the minus 2 gamma. Okay. So, what does that tell us about other relationships with these coefficients? What else can I learn from this? Yeah. Yeah. So the response was beta and gamma should be the opposite of each other. One should be the negative of the other, and indeed that's true. So the second thing that we learn from this, and I'm going to write it in a slightly different way, but it's exactly the same information, is beta plus gamma equals 0. So aka beta plus gamma. So that's one thing we learned from this. And then the last thing, what do we learn? Yeah. Okay, good. So again, I'm going to write it in a slightly different way. I'm going to balance the coefficients of the exponents here. And I'm going to say that 1 better equal minus 2 gamma, right? So, aka, it's not really the right way to describe it, but this tells us that gamma equals minus 1/2. Gamma equals minus 1/2, then beta equals plus 1/2. So what does this let us do? It's told us, in fact, the relationship of the period, which we plausibly said might depend on these three parameters. Right off the bat, we learn it isn't dependent on the mass. We learn that it is dependent, I should put a proportionality here, I should say that it's proportional to the length to the power beta, and it's also proportional to, I'll put it down here, to the local acceleration due to gravity to the power of minus 1/2. Let me combine that together, and it tells us that t is proportional to root L over g. So this is a result you might know. It doesn't give us the constant of proportionality, but it's given us a tremendous amount. Just by dimensional analysis, and some plausible inputs on what the period of the pendulum might depend on. By demanding dimensional consistency, matching coefficients in terms of the individual dimensions, we immediately learn that the period of the pendulum has this type of dependence on the length of the acceleration.